Problem 2.55. At room temperature of 20 degrees Celsius, a zero point 0.5 millimeter gap exists between the ends of the rods shown. At a later time when the temperature has reached 140 degrees Celsius, determine the normal stress, the aluminum rod, and the change in the length. So first is we must identify the given of the problem. These are the given values. So we must find the normal stress and the uh, change of length of the aluminum. So first we must find the change of length due to temperature, which is equals to the length times the uh, thermal coefficient at the change in temperature. So with this equation, we substitute all the given values. We get the change of length due to temperature, which is equals to 1.347 times 10 to the power of negative 6, or 1.347 millimeters. So the next thing we'll do is to draw the equilibrium diagram of the compressive force of the rods. Now, since it's compressive, therefore we all know that the constraint imposed, so the max elongation is equals to 0.5 millimeters. So the change in length due to the force is equals to the change of length due to temperature minus 0.5 millimeters. Then we substitute the values, we get 0.847 millimeters, or 0.847 times 10 to the power of negative 3 meters. Then due to compressive force, the load P is given by the equation. The change of length due to load elongation due to due to force is equals to the summation of force times the length over the modulus of elasticity and the cross-sectional area. So substituting with the rods, the length of aluminum over the cross-sectional area of aluminum times the modulus of elasticity of the aluminum, plus the length of steel over the cross-sectional area of steel and the elasticity of modulus of elasticity of steel. Then we equate the equation to the force, which is P is equals to the change in length due to force over the length of aluminum over the cross-sectional area of aluminum and the modulus of elasticity of aluminum, plus the length of steel over the cross-sectional area of steel times the modulus of elasticity of steel. Then we substitute all the given values. We get the value of the force equal to 232,389.8917 Newton. So with the values that we already have, we can now compute for the normal stress, which is the first required in the problem. So the formula for normal stress is normal stress of aluminum is equals to the negative force over the cross-sectional area of aluminum. The formula is negative because the force is compressive. Therefore, it must be negative. Substituting all the values of force of the cross-sectional area, we get negative 116.2 times 10 to the power of 6 Pascal, or negative 116.2 megapascal. Then we find the change of length of aluminum, which is equal to the change of length due to temperature minus the elongation due to force. Then we substitute all the given values and we get the value of the change of length of aluminum is equal to 3.632 times 10 to the power of negative 4 meters, or 0.3632 millimeters.